Welcome back to the session. Good afternoon, all. So we have with us Professor Suresh Neethirajan, who is a professor and university research sire in Dalhousie University. So Professor Suresh Neethirajan will be presenting with us his talk on the topic Digital Livestock Farming 2030 and beyond. Over to you, sir. Thank you.
Okay, thank you. The Department of Data Science, Dr. Vadivu, and all the faculty members for hosting me here today, and also to explore the collaborative opportunity between Dalhousie University and the SRM, with the main emphasis on looking at offering a course, perhaps academic without borders, creating a joint partnership in terms of connecting the dots, building a bridge between computer science, animal science, and agriculture students. Thank you for this opportunity. I also note Dr. Professor Tushar Mohanty from NDRI Online. Welcome, and thank you for joining, Dr. Mohanty. So we have written 3 books. You can go to Amazon India and search by my name. You would see these 3 books all about livestock. One is, how do we go about using data analytics and computer science for solving problems in livestock farming? It's primarily written for a first and second year animal science students within mind. So different kinds of statistics, ML models, all are I explained in the From Herds to Insights book. I also wrote a book called Metaverse for Modern Animal Farming. It talks about augmented reality, virtual reality, deepfake, digital twins, and a variety of upcoming technologies that can offer build solutions that is we usually think, hey, it's not practically possible to solve. Those kind of problems can easily be solvable using these metaverse-based technologies. I also write poems. There are about 55 poems I have written so far in the interface of artificial intelligence, big data analytics, and livestock farming. So you can find this poetry book also in the Amazon website. Very briefly, why we do what we do. When we look at the it just shows it's a sharing here.
If you share a window, share the entire screen.
Is it better now? Can they see? Yeah.
So you can stop sharing and share the entire screen. Stop sharing. Share. And go for the last tab, the entire screen.
Is it better now? Okay. Thank you. So why we do what we do? So when we look at the formula, even when we as a human being or animal, we always look at this, the interface between phenotype, genetics, and environment. So P is always equal to G plus E. For example, an early life experiences dictate and decides the later life behavior. For example, even in humans, if you closely observe, some people may be a bit aggressive, some people may be easy to get along with. So more often, if you talk to a psychotherapist, you would find that the childhood experiences, the parenting and the relationship matters significantly. So it's the case with animals, how the animals are being taken care of, whether it's a pig, a swine, chicken, a poultry, dairy cows, the early life really dictates the later life stage. So studying behavior and also the interface of phenotype in the relationship to the environment is very, very important. We live in what I would call as a VUCA world, volatile, uncertain, complex, and ambiguous. So we just came out of a COVID situation just a year and a half ago. So we are still looking at, if you are staying here in a PG or in your flat, you come here to the university today morning, see the number of things you have to overcome as a barrier: traffic, congestion, environmental pollution, social pressure. You want to do something, and there is an expectation of something. There are many things that's happening. So how do we overcome all of this? This applies for any industry, including the livestock farming industry. So how do we create profitability to the animal caretakers, farmers, at the same time cater to the needs of the individual animals, whether it's a small scale farmer or a large scale industrial production facility? These are some of common goals and challenges we have to really look into it. Recent market research and statistics clearly shows that in the next 5 years, we are 2024 now, until 2028 and 2029, artificial intelligence plays a big role in almost all domains it has touched. We have recently Gemini was released by Bard from Google as competition to Chat GPT. There are many new large language models, generative AIs are being explored. So AI plays a significant role in agriculture also. It's about almost a 25% annual growth rate on a year-to-year basis. It's very significant. So everybody has to embrace it. We don't have a choice. There are many reasons behind looking at these big data analytics and AI. So most of the time what we do is we react. For example, the COVID situation happened, and then we looked at, oh, you know what, we have to find out subclinical, preclinical diagnostics, or even 6 months before a disease incidents happen, can we be able to develop a veterinary diagnostics? How do we develop an artificial intelligence based model that would take into account to run what if scenarios, to tell us, to be able to predict situations? We sometimes we look at from a single perspective. Maybe an analogy would be you are a faculty member, or maybe you are a junior scientist. We look from a particular perspective, and then the VP research of that institute look from a broader perspective, because they get many information from multiple sources. So how do we as a end user or at a particular level go from that limited viewpoint to a holistic 360-degree viewpoint? So that's very important in developing solutions. There are factors that challenges and that dictates the development of solutions are, for example, just a few years ago, maybe 10 years ago, not only in North America, here in India also, people mostly look at price. If you go to a supermarket, you buy a animal product, a cheese or a paneer or a ghee or a dairy product, you look at the price. Hey, you know what? This is a cheaper, 5 rupees, I go for that. But now, no, we also look for, hey, this has this many percentage less fat. So we are looking at, okay, there is a bit of environmental sustainability consciousness among the buyers. So that factor has to be taken into account when we develop solutions for modern animal farming. So we talk about the big data all the time, but where does the data actually come from? So they come from three different B's. One is a sensor technology or biosensors. And then the second one is, which is a derivative of those sensor technologies, big data, and then blockchain. When we combine many of these sensors in a supply chain system, we develop solutions using blockchain for industrial production, from a raw material to a particular end product. So all these has to be taken into account in enabling solutions for improving the welfare. Of course, nowadays, when we look at the landscape, because of the population explosion, 7 billion to 9 billion, the geopolitics as well as the ownership of the farming also changes. It used to be very small, fragmented. Now, many are moving here in India, especially from rural area to cities, and the children, second generation, third generation, they are not interested in farming anymore. So there is a bit of lack of affinity towards a traditional farming. So which means there is a possibility to create a co-op type farming. How do we combine multiple farms of different sizes together, still create equal profit for all the stakeholders and owners. So the models of farming is slowly changing, or at least looked at here. So it's the case in Europe as well as in North America. How do we take that into account and cater? We also have a challenge of what we call as profit margin. When we look at the profit margin, it's becoming narrow and narrow. So we are looking at adding more values, uh, uh, finding new ways of resource utilization. So still farmers can meet the profit accordingly. So where are we at this moment in terms of collecting data? We look at the cows here. This is from one of my publications 4 5 years ago. There are many sensor technologies has been developed. For example, when a cow exhale, whatever that comes through the exhalation, the component or the composition of the air that's coming out has a lot of telltale signs. It is an indication of the gut, the rumen microbiota. So we can actually find out what's going on in terms of the pH, the other related indirect information about the health of the physiology of the cattle. For example, the blink of an eye, it can also provide a lot of information. I'll give you an example down the road. So facial expression data. So when we look at the face of the pigs, cows, and chickens, unlike human beings, they have a lot of fur, less muscle. So the features are very different. So we can actually extract information to understand the mental capacity and the makeup of these animals. Vocalization data, of course, it provides moo calls. Cows make different calls, clucks and squawks and purrs of chickens. So the sounds can also provide a lot of data that can we use natural language processing to actually explore and decode the communication of these animals. Activity, we put accelerometer sensors. Cows move around, how long they are walking around. We put pedometer on the legs. We measure what side of the body the cow is lying. Is it right side or the left side? How long it is walking and how long it is sitting. How much time the feeding happens based on the rumination and the activity on the snout facial region. So there are a number of ways data can be acquired to understand the behavior, physiology, health, welfare, and a lot of parameters in a non-invasive manner from these livestock animals. So, of course, we have multimodal data. Data comes from images, videos, numbers, biomedical. We put a belt that can measure heart rate, respiration rate. We acquire the data. We use thermal imaging to acquire the heat signatures. So how do we collect? We have collected multimodal data: audio, video, sound, images, frequency, amplitude, energy, signals. So how do we infuse and create fusion of these data to create a cohesive, synergistic way of developing a trends and pattern in truly understanding what that animal is going through. So computer science plays a significant role. AI helps quite handy in solving some of these problems. So when I use the word phenotyping, so of course P is equal to G plus E, but sometimes we always look at from a gross level. We collect data, maybe the per day data or per hour data. But with the advent of the new technologies, we are also looking at certain level of data. For example, you are all, maybe some of you are wearing here Apple Watch or Samsung smartwatch. You can measure your own heart rate, respiration rate. So when you wear these smartwatch devices, or even your phone can do that. If although it's sitting inside your pant packet, you just move around, you walk around, it constantly records whether you're sitting, what kind of vigorous activity is going on in your body. Those kind of information is recorded subtly using the accelerometer built in your phone. So if we go from a very gross level to a certain level, instead of hour per hour data to minute by minute or even moment by moment, there are lots of information buried in there. So these information can be unraveled to connect to some of the questions, bigger questions we are looking at in improving the welfare, bringing down the climate change. For example, 1% rule. Maybe you have heard this 1% rule. For example, somebody wants to lose weight. Okay, that person is 90 kg. He or she, they or them, they want to lose weight, body weight. So they don't have to do drastically. It could be a 1% small change. For example, cutting down sugar, or instead of taking a lift, I will take the staircase at least in the morning, if not in the evening, because I'm tired. So small little changes. So when you look at these small little changes every day, not only once. So the next day you increase that 1% to another 1%. The third day you increase to another 1%. So this is a cumulative effect is 37 percentage. Actually, 37 times you can reap the benefit within the 365 days. But if you slack 1% every day, within a few days, we can go to the ground level. We'll lose that capability. So there is a formula of 1%. So the similar concept here in data analysis, we look at smaller signatures, small buried telltale signs, and look that information to further unravel, analyze, and look at from a holistic perspective. For example, it's a clinical state, high-level behavioral indicator versus low-level futures, sensors, and then we combine, integrate, fuse these from the context of animal, because we cannot anthropomorphize. We as a human being, we may not fully understand what the animal goes through, what it needs, what are the actual reality from the animal's perspective. So without wearing the human lens, can we be able to imbibe into what the actual animal goes through and use that to collect the data and analyze, then we can really hit the ground running. I'll give you a couple of examples very quickly. This is a study we did with a collaboration with Germany and Netherlands. How do you find the sex of a chicken? People have looked at many things. They looked at the shape and size of a egg of a chick, and then they looked at the temperature. They put a stethoscope on the surface of the eggshell, try to measure the heartbeat. They put the egg in a little small boxes, and then there is a odor volatile gaseous mixtures came, tried to measure. Nothing worked. Then there is a new technology for the past few years. What people use is just drill a 2-millimeter hole on the eggshell, and then they insert a small pipette or a needle inside, take a small amount of sample and do an ELISA, enzymatic ELISA test, to look for specific hormones associated to the sex. So the gonads, the male versus female chicks, the urine, when it comes from the male chick inside the egg, is an indicator of the sex organs, of whether it's a male or a female inside egg. So why it's important? Because France and Germany has created a new law. They say that you cannot kill the male chicks because it's a violation of animal welfare and ethics. There is also, it takes about at the age of 10 or 11th day after the chicken hatched the egg, it's scientifically proven that at the 11th day, the chicken can feel, because the heart has developed, the feeling component has occurred. So what we did is we came up with a new technology. Even drilling hole doesn't work all the time, because there are millions of eggs and we cannot drill all millions of eggs and take fluids. So we use NIR hyperspectral imaging and Raman imaging, and put it in a belt conveyor and scan thousands and hundreds of images, and we developed a model using big data and AI. We can see some of the samples here. So we can see also the visual inspection of gonads on day 16 of incubation to differentiate the male and female here. So again, it's a very, very large data. There are two types of spectrum. One is the Raman spectrum. Another one is NIR hyperspectrum. We use big data analytics and different approaches to bring down the time to results in differentiating the sex without having to drill. The idea here is NIR has the capability to penetrate up to 10 micron thickness inside the eggshell. So we look for biochemical signatures inside the eggshell by rotating at different regions of the egg. in combination with Raman, we were able to find out. We also work with the company, again, this is a Dutch, Netherlands-based company. We developed what we call a pill that can be swallowed by animals that can measure pH, temperature, and also a little bit of the microbiological components in near real time, and it can store it for some time. So it's not yet feasible for chickens because of the body size, but this has been demonstrated for pigs and cows. So a lot of data, again, it's a non-invasive, minimally invasive. The cow and the pig has to swallow, it remains for a day, and then when it gets ejected, it comes outside from the dung. People collect that capsule. It has a time and date stamp. So we know based on the experiments we have done what kind of feed or supplement the cow and the pig has taken. And then we correlate that information along with other behavior, blood samples to understand the nutritional aspect in designing new supplement and nutrition for these animals. So it's a combination of sensor development, a bit of technology in data analytics to understand. So we have developed a few machine vision technologies. For example, here it's a chicken detection tool. The idea here is we can actually count how many chickens are present in a coop, how many times they are making a trip to a feeding station, how do they talk among themselves, with the social network analysis, and so on and so forth. So we can predict aggression behavior as well as pecking behavior based on the activity pattern, but also we can understand the in terms of designing the animal husbandry, we can go about determining designing new solutions using this. For example, in this picture, if you see here, there are 3 circles at the bottom. It has 4 different quadrants in different colors. So we can clearly see that they are all different shape, which means that there are n number of birds in each of those quadrants, depending on the changes in the airflow, the humidity condition, the availability of feed. They what we call as a migration coefficient index. They try to move to a particular region at a particular time. So we using this, we did a longitudinal study for several hours, and we came up with a mathematical model of social network analysis in relation to a variety of environmental enrichment, as well as the other related feeding and water availability, frequency, hygiene quality, air quality, etc. So this way we can actually quantify the phenotyping more precisely. We also went ahead in terms of understanding the stress as an indicator of welfare, as a development of non-invasive measurement of stress. So what we did was, for example, in a commercial production system, especially in Europe and North America, when the eggs hatch and the chickens come out, they never see their mother. At least in country coop at the backyard, we can clearly see there is a relationship between the mother and the chicken eggs. So because of this lack of social imprinting process, they basically look at each other, and then as soon as they come out, they start pecking and they make noises. They try to communicate with each other. They don't know how to really what's good, what's bad. Is it a food? Is it a poop? They just try to peck, and then learn based on trial and error. So this has a certain implication in terms of welfare. So we did a longitudinal study of about 16 weeks of different laying hens to understand how stress manifests and emanates on the laying hens using a combination of visual stress as well as a audio stress. So we suddenly open an umbrella when the birds are placed in a coop. This is a visual stress. They kind of freaked out and move away. And then there were a bunch of students taking a very large thermal camera, collecting thermal images. And then we also played sudden wolf and dog barking sound, audio stressor. And then we looked at how these birds started reacting from day 1 to almost 16 weeks of their age. We also looked at does a repeated stress influence and introduction of stress, do they adapt to that capacity? how does the adaptation physiology develops. Then of course, we collected the audio sound vocalization as well as the thermal imaging. Here we can see some of the images of so the question we were looking at asking is, can we be able to determine the stress based on the blink or the wink? Yeah, sometimes we say, oh, that guy is winking me. But maybe the wink can provide many buried information. So unlike human beings, we have, just a vertical lower and upper lid. Birds have vertical lid. We call them as necessitating membrane. They kind of open and close. If you closely look, especially chickens. So the signature of the heat, the amount of the time the blinking happens in respect to the stress plays a significant role. So the blink of an eye can also provide information about when the stress is coming from the bird, whether it is because of the stress or is it because of the bodily physiological changes. So we collected cortisol, lactate, and blood samples and did a very detailed analysis. We also used thermal imaging to acquire a variety of how the facial heat signatures changes in the comb region, surrounding the heat in the beak, as well as on the body of these birds. So the chickens tend to display more full blinks. Again, we can differentiate whether it's a full blink or a half blink after a stressor. So laying hen chicks never blinked without a gaze shift, which means they tend to move their head to the sideways before they blink. So that also plays a role. So this is another example of how do we quantitatively examine the relationship between the facial temperature and blinking in relation to stress, because it can tell a bit more about what we call as emotions. Here we can see some of the examples of the thermal imaging videos, how the heat signatures are actually distributed all over the body of the chickens here. So surrounding the face region, the comb region, the feathers. Of course, sometimes feathers tend to hide because the actual thermoregulation happens under the feather, but the beak is made of what we call as keratin, a proteinaceous material. The inhalation, exhalation happens through the nozzle, which is closer to the beak, and then the comb region. So this variation in different facial parts of the chicken tells a lot of information about how the indicators of stress can happen and how do we go about determining the stress. Again, it's a challenge here is we studied 60, 70 birds. If you look at the poultry industry, we have about 3,000, 4,000 birds at a time from a camera field of viewpoint. So how do we scale it up? How do we, again, the distance between the object to the subject varies. So those are some of the challenges that yet need to be addressed. So we also collected a variety of vocal signatures. We introduced few birds to avian influenza virus, and then a healthy, neutral as well as unhealthy birds after exposure to avian influenza respiratory disease. That's one experiment. We also conducted two different experiments. One is the stress-induced visually and audio, and collected at different time points, control as well as the stress-induced pre-stress and post-stress. The third experiment, we actually went to industry, about 16 different commercial farms, and collected a lot of data. So the idea here is the birds all the time, they talk to each other. So can we be able to really decode? So we employed a couple of models, hugging a Marco model, whisper model, different types of natural language processing to actually understand the language behind these words. So it's a lot of behavioral scientists, ethologists, neuroscientists were involved in this large-scale project. So, for example, the preliminary results clearly indicate distinct differences between healthy versus unhealthy bird. Sometimes when we try to exactly translate or equivalent translation of human languages for the healthy bird, when they just peck, 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 and then make certain clack, squawk, purr, clack, squawk, purr, like that they make the noise continuously. So when we translate using these artificial intelligence NLP based models, it says, I'm going to the next room, I'm moving around, I'm okay. That's the equivalent terminology we can, semantics. So we put what is the intention behind the emotion, the context behind these noises. These are the type of equivalent words one could decode. But at the same time, when we actually decode some of the unhealthy avian influenza respiratory noise, it clearly shows hospital, hospital, hospital. So then we know that hospital means if somebody is stressed, that's why they, so it's their own way of asking for help. Again, people may object, oh, you are making it up, this is not possible. But so what we did, we again recorded, we understand the frequency, pitch, amplitude, the gap between the frequency, how much of energy is being expressed under each of those calls. Sometimes they make food calls, sometimes they make alarm calls. If there is a hen and a chick, the mother hen would call only to that particular chick. If the chick from the other hen is present, they don't respond. So there is a pattern, there is a involved in terms of animal cognition, animal communication. So we recorded using a variety of videos. So it's still more work to be done. It's kind of surface scratch, but this is a very, so this area of research is called digital farm animal bioacoustics. So it's happening again. Some of the instruments are very expensive to be able to analyze. Not only collect, but also computational resources are humongous. Then there is a lot of collaboration is needed. It's not a one discipline specific. Neuroscientists, ethologists, behavioral scientists have to definitely involve, else it will be easily dismissed. So we have some collaboration with United Kingdom, some from United States, of course. There are 3-4 country people involved in decoding animal communications for cows and chickens. Cows, we have moo calls. Sometimes they tend to express, they are very passive aggressive. Through licking, they display their liking or disliking. If they are very vigorously licking, they tend to display their, demonstrate their ability to, territorial ability. For example, if they're about to call, they try to make specific call, vocalization. At the same time, they try to start licking vigorously. It's a way of telling that, hey, give me more space because I'm going to give birth to a call just about 2 hours before. So which means there is an immediate need to provide additional space, a bit more privacy for the calving to happen for the cows. Of course, we did a bit more work with the lighting in Amsterdam. Here in Mumbai also, there is something called red light district. People go for sex. So red is always associated to sex, but in India, being a spiritual country, red is also associated to holiness. You know, Ma Kali, you can always see wearing red sari and red bindi and so on and so forth. So red is a very dynamic, powerful energy. So the wavelength of light of LED dictates the behavior of the chickens, of course, for cows too, but it's not that gross. We have to look at the smaller subtleties, smaller change in the wavelength. How do they influence? So again, we did a study for 12 weeks of 3 different light to see, how, for example, in this case, blue light brings more calm and a bit more comfort, and resting behavior is predominant in the chickens compared to white and red. So we were able to characterize and take videos systematically for about 23 characteristics, behaviors of chickens. For example, there is a behavior called mouth-to-mouth feeding. One chicken would take a peck, and then the other chicken would not peck from the feeding. It would try to peck from the food from the other beak. So it's a unique behavior. Sometimes after feeding, within exactly 12 minutes, 10 to 12 minutes, depending on the age group, they tend to perch and then try to doze off, like to have their own zone. So there are unique characteristics based on the different age level, different breeding conditions. We were able to create what we call as figures of merit to show some of these aspects. Emotions also plays a key role. We were able to develop some AI-based tools to determine emotions from cows and chickens. I'll go very quickly. But again, it's not. It's a lot of work was involved. We collected many data from Michigan and Europe, and of course in Canada, quite a bit of data. So the idea here is we were able to classify 13 different emotions: frustration, happiness, neutral, aggression, alert, relaxed, and so on for cows and pigs. We closely collaborated with a scientist from Mike Mendel from UK to come up with some framework, because Paul Ekman is the guy who actually introduced psychology as well as human emotions makeup in 1965. We are in 2024. We learn from them, but we don't use entirely the same can be applied for animals. It has to be, the framework has to be changed, because we would then look from the lens of the human beings. So the about 78,000 images after denoising, 1,530 videos were utilized in this particular study. An example, just a small video clip to show how the system works. So what we call here is a valence. Valence means the at a particular timestamp, how the intensity of that emotion increases or decreases. That's a valence component. We also have the ability, because it's a time, it's a combination of multiple facial features. It's not just eye alone. For example, the eye white regioning, if it becomes much bigger, it's a surprise or a shock. Ears, the ears of the cows and pigs, sometimes they're symmetrical, asymmetrical, droopy, relaxed. So they tell a certain sign. There is a bit of tightening that happens in the snout region. So we cut a head of a cow and a pig, and then did a little did a CT scan, and then use that information to build a model in collaboration with Clara Mancini from UK. So it's a very complex, multidisciplinary people were involved in developing this particular tool. Recently, we also developed a tool called Mood Tracker. It's a biometrics-based bovine facial ID. The idea here is, if you look at the nose region of the cow, it's called muzzle. So it has a certain shape, certain geometrical features. But the goal is, can I identify this is Lakshmi, this is Geeta, this is Janaki? So can we be able to individually classify and identify cows based on their facial features? So that was the goal of this. Of course, we developed an app using PYQT and YOLO VI based model. So it's I think the second iteration is currently happening. This is just some of the preliminary results. Here we can see that the it works. We also looked at different breeds, Holstein versus Jersey versus different landscape. Can the app can still detect a cow as a cow, and also differentiate between individual cow, and also can it count how many of them are present using an app? So it's an app development for a desktop and Android-based development using YOLO V8 and PYQT and other based algorithms here. Pig, we did a bit of work for pig. What we did was, we were interested in understanding the biological limit. For example, pigs gain from maybe 30 kilogram to 300 kilogram in 6 months. So that's a lot of body mass gain in 6 months in a shorter period of time. So we call this as a violation of biological limit. So the heart of the pig can hold the stress to a certain extent. So after the pig swine is grown, here in Europe and North America they do is, they ship the pig in big trucks to the slaughterhouses. So if there are 300, 200 pigs in a particular truck, before they reach the slaughterhouse, during the transportation itself, like 5 dies. So we call them as dead on arrival. So how do we avoid this dead on arrival problem? In consideration of this violation of biological limit related to the heart rate. Again, everybody's profit more oriented. So how do we infuse welfare without sacrificing the profitability? So we were looking at developing new strategies, pig transportation, improving pig welfare, pig physiology using AI and big data based approaches. So we work with multiple stakeholders and partners. We use thermal imaging. We put a little belt, it's basically like a tattoo kind of thing, sticker that sticks on the left leg of the pig. It collects respiration rate, heart rate, and acceleration due to gravity. Harini was showing some results today morning, a portion of the data from this particular experiment. So we were able to come up with new ways of how do we manipulate the shipping time and also change the frequency of the feeding. To be able to prepare the pig for the transportation a week in advance so that they remain in healthy condition. So it's a very multifactorial. So we came up with a large list of recommendations of what to do, what not to do, based on the some of the model results we have got. So the sensor data can also help to map resilience indicators and boost livestock well-being. So again, when we look at the emotion in combination with physiology, along with behavior and health and welfare has to be taken into account. For example, if you have cows and pigs and chickens, sometimes there are two cows. They were born to the same mother cow, so they have become a calf to cow. They are exposed to certain stress. One cow immediately, quickly demonstrate resilience and come back to the normal healthy stage after exposure to disease. The another cow take a longer time to come back to the ground zero after it exposure to the disease. So why? They are of the same genetic trait. Maybe the environment may be a little bit different. So why? What is the reasoning behind this resilience? How do we assess this? So big data comes in quite handy to solve some of these bigger problems, bigger questions. This is some of the tattoo type of sensor we have been in collaboration with a company called TNT in Netherlands. It's like a little sticker. You put it there. You can measure 3 different parameters simultaneously. Very lightweight. Only accelerator or accelerometer is a bit heavy. So there is a bit of sensor development work also happens from our side. Of course, we have to really consider here in India, whatever these technologies developed in Europe and North America may not be applicable here. We have to look at the scalability because farm size is smaller, resource use utilization. Conditions are different. It's very cold versus hot, very rugged. The literacy, how do people easily handle technology, digital divide that we have to consider. Some people are very, very easy to embrace the technology. Some people you need to really sit with them and educate them through extension activities. How do we overcome digital divide so we embrace, irrespective of the education the farmers and other stakeholders are getting? We have to really consider that. So the individual human qualities, cultural factors, animal. For example, in this picture, we can see we love the cat. The cat is or a dog. It's part of the family. But the chickens are at the other side. Do we give the same attention, care for the chickens? No. So are we, as a human being, are we treating all animals equally? We here in India, of course, we say a cow is gomata, but cow is basically eating microplastics in the streets. Like resource is a bigger issue. There are population explosion is a bigger issue. So we have to consider from a holistic point of view of socio-economic, political, as well as the cultural factors has to be taken into account when developing solutions. We also have to reflect as an individual human being, are we really genuinely caring about the welfare? Can we be able to ask the animal in the way they can express themselves? What is it that animal exactly needs? Using the technology and decoding that to develop real, genuine solution using some of these. So we have to carefully look at some of these aspects. There are other few projects we have been working on. Umang is working on dairy industry climate change aspects. Harish, he he is working on behavioral analysis using large language models like Chat GPT and Gemini and so on for dairy cow behavior. Shubhangi is working on biometrics development for cows. Harini gave a talk today. Venkat is working on decoding emotions from poultry bones. So these are some of the past students from my group. So it's been a wonderful journey. Of course, we have done only a little bit, much more that need to be done in the livestock area in infusing technology, creating a beautiful interface between AI, big data, animal science. Thank you so much.
Yeah, we want to express our heartfelt appreciation and gratitude for your remarkable session, sir. We gained a lot of insights on, and even I saw a different, multiple dimensions of livestock farming, which gave us a lot of ideas. And over to participants, any questions?
Good evening, sir. I feel like I finished the science class. After the science class, we feel yes, our brain is fulfilled with a lot of technologies, lot of methodologies, research points. So after the session, I feel like my science class is over. So lot of insights to work forward, lot of experiment, lot of things need to do. Yes, finally everything is affordable. People can afford in Canada. Extension activities are required. A lot of new innovative digital tools are to be prepared. That will be here in according to our climatic conditions. A lot of things are required to do. Thank you for the wonderful section, sir. Because yes, before this, not much of idea about these digital tools utilization in our livestock farming. But today it was wonderful.